Good morning, everyone. I'm Chuangyi from Huazhong University of Science and Technology. Today, I'm going to introduce our research on graph pattern mining systems. In this work, we aim to solve redundant computations problem in graph mining and show how the set data flow efficiently removes redundancies. Graph pattern mining is widely used in real-world applications. In an input data graph, it seeks out subgraphs of interest known as graph patterns. Due to the explosive size of search space, graph pattern mining is commonly known with high computational complexity. How to efficiently traverse the search space is essential for good performance. In recent years, general-purpose graph pattern mining systems have emerged to target high parallelism and optimal search space. In the embedding-centric paradigm, each intermediate subgraph instance is viewed as an embedding. It extends from each vertex to eliminate the embeddings level by level for extracting the patterns. Complex isomorphism checks are performed to determine whether the subgraphs are wanted patterns. Despite the high parallelism as the embedding-centric embeddings are basic parallel units, this approach consumes a lot of memory and has time-consuming check operations. The pattern-centric paradigm instead uses the pattern structure to guide the exploration, avoiding storing all subgraph intermediates and isomorphism checks. Based on the structural information, these systems typically follow a matching order of pattern vertices to explore subgraphs. At each level, the exploration conducts set operations on corresponding neighboring needs of the partial subgraph to generate candidates for the next level. Compared to the embedding-centric ones, the exploration of unnecessary partial instances are avoided. Thus, the workloads are reduced to a large extent. Our work is also based on the pattern-centric paradigm. Given the matching order, existing works typically execute the nested loop of set operations to compute the final subgraphs. The candidates of each pattern vertex can be generated through a set formula. Initially, each data vertex is fed into the first loop. Each loop will then generate a series of partial subgraph instances mapping to the graph pattern. Existing works mainly focus on optimizing the matching order to further reduce workloads. They also use the symmetry breaking rules to avoid automorphisms that enforce partial orders among vertex IDs. This is because an exact subgraph instance might be mapped to different pattern vertices and cause invalid workloads. For instance, the subgraphs 2304 and 2340 are identical. Symmetry breaking ensures that the subgraphs discovered are unique. In conclusion, existing pattern-centric systems focus on the reduction of the search space. In terms of the search tree, many branch paths are filtered by the proposed optimizations. However, even in an optimal search space, redundant computations exist as repeated same set intersections, which have a great impact on the performance. These redundancies reside within the search path and cannot be removed using existing search space reduction methods. Specifically, we divide the redundant computations into two categories, based on whether they are performed on the same neighboring needs from the same subgraph. Consider a partial instance mapped by white vertices, and we want to compute the black vertices collecting to the same white vertices. In the edge example, these computations will all be performed at the intersection of neighboring needs of 1 and 3. These are just explicit redundancies. In the implicit redundancies, although the computations are operated on different sets of pattern vertices, the exact computation on data graph vertices may still be the same. For instance, in two triangles, 1, 2, 3, and 1, 3, 4, the same set intersection on vertices 1 and 3 are performed for both subgraphs, even the subgraphs are different. In this example, the same set intersection on vertices 1 and 3 are conducted 4 times in total. In fact, when it happens for the first time, we can store and reuse the results. This is challenging, however, because the redundant computations are spread during runtime and hard to predict. In particular, we examine various patterns and keep track of the number of set intersections specified by operand's ID. In the mining procedure, over 80% of the computations have been repeated. careful readers may notice that some explicit redundancies may be recognized before computation in the compilation time. That is, if the set formulas of two pattern vertices are the same, then we can rewrite them into one single formula. They have equal substructures in terms of the graph layout. However, simply depending on the structural equality is insufficient. In our experiments, moreover, 60% of the redundancies remained after the rewriting optimization. This is due to the fact that many implicit redundancies cannot be tracked before the computation. Furthermore, some explicit redundancies exist, such as the set intersections on an inverted subgraph instance. Luckily, instead of structural equality, we take a deep dive into the operands level of the set formula and observe two types of computation similarities. The first one is the static similarity. Multiple operands of a set formula might be shared. Rather than just reusing the output results, we can take use of the similarity of inputs as well. This is a spatial view of the static pattern structure. The second one is the dynamic similarity that reflects the runtime characteristics. We reordered the data graph vertices by decreasing degrees and counted all vertices involved in computations during runtime. The majority of computations are observed to be concentrated on a small number of high-degree vertices. These observations allow for prediction and reuse of duplicated inputs and outputs during runtime. We can focus on tracing these high-degree vertices and prioritize them while scheduling. To effectively utilize the final grain similarity at the operand level, we need a new abstraction rather than just the set formula to describe the computing procedure. Because all neighboring lists and candidates of a vertex can be represented as sets, we propose the perspective of set Dataflow in this paper to take advantage of the data reuse possibilities at the operands level. The set Dataflow is a directed graph that indicates how sets are transferred between operators. It enables fine-grained pattern analysis by decoupling the set operands and operators. The figure depicts a Dataflow abstraction for set formulas 1, 2, 3, which contain two operators for fetching neighbors and one operator for intersection. The edges of the Dataflow demonstrate how the inputs and outputs are transferred. The shared source nodes indicate the possibility of data reuse. By maintaining unique operators in the set Dataflow, we can remove explicit redundancies easily. We can see that a simplified set Dataflow can significantly reduce the number of required set operators. The neighboring lists are also fully shared. Following the Dataflow, we can cache and reuse any set to any operator. Although the concept of set Dataflow is intuitive, implementing it in the mining system is difficult. It confronts challenges ensuring both correctness and efficiency. In this work, we designed Cyclosa, a prototype system that uses set Dataflow to eliminate the redundancies. In particular, Cyclosa accomplishes three major tasks as above. First, user input patterns are automatically analyzed to generate an efficient set Dataflow for set scheduling. The generated set Dataflow is then fed into the set operator execution engine. Cyclosa supports three basic set operators and arranges sets based on the Dataflow graph. During runtime, the execution engine collaborates with the set manager to cache and reuse the computed results. For parallel execution, the set Dataflow exploits the data parallelism by flow replicating. Initially, the neighboring sets of all data graph vertices are started concurrently. Now, I will introduce the key designs of the set Dataflow analyzer. We can extract the set Dataflow only after determining a matching order. However, it's challenging to realize both an efficient search space and minimum redundancy. As illustrated in the figure above, different ordering can result in different search spaces. We want an order with the fewest workloads. Furthermore, in order to improve data reuse efficiency, we hope that the most frequent redundant computations occur at the beginning of the processing. To accomplish this goal, we designed a two-phase pattern analysis approach that takes into account both pattern and data graph features. Firstly, we enumerate all valid degree-first DFS orders. to raise the possibility of results reuse. This ensures high-degree vertices are mapped first, and we can trace the frequently reused computations at the first time. Second, in order to choose the one with the lowest cost, Cyclosa will apply a cost estimation to all valid orders. The cost is calculated as total computations for mapping each pattern vertex. Prior works typically estimate newly produced workloads every iteration, use a static metric such as the average degree. This, however, ignores the reduction information on neighboring lists after a set intersection. To improve accuracy, we combine to use the triangle count per edge to indicate the change in the input-output size of a computation. We additionally take into account the effect of symmetry breaking by adding a reduction parameter in corresponding loops for higher precision. After the order is determined, we design a representation to store the information of set data flow. The representation has the ability to decouple computation and set data. To cover all functions, we extract 3 basic set operators. The generator has the ability to split a single set into multiple sets. The combiner combines several sets into a single one. A long set is reduced to a shorter one via the reducer. Each input and output set data is assigned a unique ID. We can then construct the sub-data flow for each set formula, using these basic elements of the representation. The final set data flow is obtained by merging the inputs and outputs of all subflows based on the same IDs. A simplification procedure is applied by conducting the flow cutting on the combiners with same source nodes. This representation is accessed by the execution engine to guide the computation. Next, I will introduce the set data flow execution engine. Existing works use the subgraphs as the basic parallel unit in parallel execution. The operator will extend and construct new subgraphs for each partial instance. The set operators are performed invisibly by subgraph operator. This mode is oblivious to the shared sets during runtime because they originate from different subgraphs. In our work, we take a set-centric view, with sets serving as the primary parallel units. Even though the subgraphs are different, the set operation on 2 identical vertices will be detected as the same computation. The set operator will take care of the input-output sets other than the subgraphs. We especially add a check function in the combiner to avoid repeated computations once the results have already been computed before. As a result, each set operator just needs to keep an individual local set space in coordinates with the set data flow, which saves memory space. However, as a side effect, the set operators are oblivious to the subgraph structure, which may result in incorrect answers. We propose a set structure that use dual IDs for identification. The set operator only needs to take care of the set ID, while the subgraph ID and operator ID are used for scheduling. Using the dual IDs, the execution of set operators is highly coordinated for correctness. The produced set results are then handled by underlying set data manager. The main challenge for the sets manager is the trade-off between memory capacity and data reusability. We maintain a fixed size buffer and selectively stores the results with a 2-phase check procedure. In particular, the priority check adopts a heuristic caching mechanism to drop results with low reuse possibilities. The caching approach takes into account 2 factors: the degree of involved vertices and the place in the data flow where results are produced. High-degree vertices are generally favored, and the results produced at the start of the set data flow are typically reused by following combiners at lower levels. Above is the design of our system Cyclosa. In the evaluation, to test the efficacy of our methods, we consider various patterns in earlier work. We also choose real-world graphs of various sizes in the test. Cyclosa is currently designed to run on a single machine, and we compare the most performant single machine systems. GraphPy has best search space, and SAMPA also reduce some redundancies, and is most related to our work. Parts of the results are shown to demonstrate the efficiency of set data flow. Cyclosa can handle both explicit and implicit redundancies and outperforms prior works in all cases for subgraph listing of single patterns. Cyclosa achieves better speedup for skewed graph, like OR, because the subgraph level scheduling in existing work has considerably different workloads for various threads. Whereas the set data flow can also use finer grade parallelism on set operations. For mining multiple patterns, we present the results of counting pseudo-cliques. Cyclosa can mine multiple patterns simultaneously because they are all organized into one data flow. In this way, we can not only remove explicit redundancies due to the structural similarity, but also reuse implicit redundancies across multiple patterns, which prior works cannot. In this slide, we test the effects of caching on motive counting. The non-caching approach can only solve explicit redundancies. We may conclude that Cyclosa reduces more redundancies than previous approaches, especially for implicit redundancies removed by a hybrid caching mechanism. When we increase the cache capacity, we see a slowdown in performance increase. This is due to the fact that more capacity also means higher memory access latency. We also test the scalability of Cyclosa with increasing number of threads. Cyclosa scales well with physical cores because multi-level parallelisms for the sets are explored. We also support fine-grained load balancing scheduling among sets. However, hyperthreading is less effective than previous studies since memory access contention becomes an issue when maintaining the sets. Finally, we will go over the major overheads of Cyclosa. Despite the fact that storing computation results for reuse may incur additional overhead, we maintain a fixed small size to store sets that only contain highly reusable results. Furthermore, the set data flow is processed in a DFS fashion, and each set operator will reuse the allocated set space in terms of data flow building time. This includes pattern analysis and data flow creation. Because the pattern size is usually small, is relatively short in comparison to the entire execution time, which typically exceeds hundreds of seconds. In conclusion, in this paper, we point out the redundancy problem in the pattern-centric paradigm, which prior works often omit. Through the observation of computation similarity in set operands from both spatial and temporal perspective, we discover chances to reduce both explicit and implicit redundancies. Then, to take advantage of the computation similarities, we propose the concept of set data flow and design the prototype system Cyclosa, which includes a redundancy-aware data flow analyzer, a stat-centric execution engine, and a memory-friendly set management substrate. Cyclosa reuses the redundant results efficiently and outperforms state-of-the-art in various situations. Above is the presentation. Thank you for listening.